the Capit Center YouTube account page, and they'll get the video.
You look very tacky.
The top of
I'll
the
have
page.
to figure that out. Okay.
You're warmer. She's so cold.
Because I don't have access to any of the things that I could send it to. So.
Okay.
I have access to it.
So thank you all for coming today. Today marks the beginning of our 10th anniversary year as the Capit Center. The Capit Center was formed in March of 2007. And to celebrate 10 years of STEM education research, and building on Capit's ideas of democratizing access to powerful ideas, the nature of technology for supporting STEM learning, building representational fluency, and bringing forward-looking curriculum reforms to scale. This year we're going to have 4 speakers whose work exemplifies at least one of Capit's 4 ideas. The most pervasive of those is democratizing access, and this morning the people who were here for the workshop heard a little bit about the work that Dr. Vahey has done around democratizing access using representations for young children. And this afternoon we're going to hear more about bringing reforms to scale as well as democratizing access. This afternoon's talk is directly related to Jim Capit's work in that it builds right out of the work of SimCalc and provides us with a view of one particular trajectory of how that work has been moved forward. Dr. Stroop has another trajectory of how that work has been moved forward, and I think it's a really interesting thing to look at all the different ways that SimCalc is out in the world now. It's my pleasure to introduce Dr. Phil Vahey. Phil is the Director of Strategic Research and Innovation in SRI's Center for Technology and Learning. His research examines the design and use of technology-based systems that enhance the learning of conceptually difficult STEM concepts, as well as how to scale up the use of the systems. Phil focuses on using dynamic representations to make foundational concepts in mathematics accessible to diverse students, particularly in the middle grades. He's also interested in the use of media and video games to make STEM ideas more accessible for preschool students. We're delighted to have you here, and we look forward to your presentation.
Thank you very much.
Yes.
So thank you all very much for having me. I'm really honored to be here. The Capit Center has such a great, important history and present and future as well. So it's really exciting to be able to kick off this 10th anniversary series of talks. And as Chandra said, I'm going to talk, well, first I'm going to talk about a little bit of an incomplete background behind some of the work we did and kind of how SimCalc was really foundational to everything else in this talk. And as you mentioned, I'm going to take one path through the story there. Walter has a different path as well. Steve Hegedus has a bit of a different path as well, right? So there are many ways it's branched out. So I don't want to make it seem like SimCalc went to this, right? This is a path that was highly influenced by SimCalc. And then I'll tell you where we're at and where we see the future. So with that, and you know, this, I'm going to talk about a lot of research that's had a lot of funding and support through the National Science Foundation, Department of Education, and foundations such as the Li Ka-shing Foundation and the Helios Education Foundation. So all this has happened with a lot of support behind it and with a large team. You see it says Phil Vahey and the SunBay team, which really are too numerous to mention throughout, but this is the group of a large number of very talented individuals. So in around the 1990s, Jim Capit had a mission of democratizing access to the mathematics of change and variation. And when he says democratization, we went back and looked it up to make sure that we weren't misinterpreting, actually, because we had a little bit of a debate about what it means. And I think it's a low inference thing to state, but perhaps still debatable, that democratization refers to an emphasis on design and development of activities for students who would ordinarily be excluded from advanced mathematics. Okay? So, and technologies, and specifically dynamic linked representation simulation, provide the basis for these new activities. So students could get into the mathematics without having traversed the worlds of symbols and deep text. And they could more deeply interact directly with mathematics and their intuitions, right? And that requires reconsidering what is taught, when it is taught, and how it is taught, right? So it's not democratization to making things more efficient, making the current curriculum more efficient, right? It's not democratization in some other ways. It's really rethinking how we teach mathematics so all students have access to the concepts. And so why dynamic linked representations? Why is that linked to democratization? Well, we have students interacting directly with mathematical objects. There's not this kind of there's a historical reason why mathematics is right now so symbolically intense, but you can get to the concepts in other ways. Right? Students can explore the effect of these interactive mathematical objects on simulations. They can link it more to their real-world knowledge and understanding. And students can investigate their own intuitions. They don't have to be told something mathematical, then practice it. Right? They can engage in how do my thoughts, how do my intuitions interact with these mathematical ideas. Now, also, when you explore through dynamic link representations, it makes very evident what is variant and what is invariant. So, for instance, very common when you talk about dynamic geometry, right? One can actually go through a large number, not quite all because computers are still digital, right? They're not purely continuous, but a large number of angles on a triangle, and notice that while the individual angles, right, may change, the sum of the angles always equals 180 degrees, for instance. We'll see in some of the work we're going to do more directly built on SimCalc, you can change the slope of a line, right? But when you do so, still the starting point of the runner stays the same. You can change the starting point of the runner, the slope of the line, therefore the speed will remain the same, right? So as you interact with these representations, what is variant, what is invariant is very important to understanding the mathematics. It allows students to make connections. I'll talk to that a little bit as well. The slope, as it turns out, seems to control the speed of that runner, right? That's a very easy connection to make. That's not so easy when you're in the world of all text. And it provides opportunities for sense making. You can actually be surprised when you're interacting, when you're exploring. And then when you're surprised, you can try to figure out what's going on and how to engage in this very mathematical idea of sense making. That's much harder to do when things are presented to you already laid out on a printed page, for instance. So we sometimes call this an intuitions first or experiences first approach, different from a common mathematics definitions first. You are told this is the definition of slope, now let's practice slope, versus let's change this line, let's experiment with this line, and so let's look at what happens with this runner, right? And oh, that results in a change of speed. How can we calculate that runner's speed? It's a very different experience than being told slope and then practicing it. And I think it's worth saying that we should contrast these versions of democratization as access to video lectures, right? There's a version of democratization where all children now, via YouTube, via Khan Academy, via MOOCs, can have access to the best algebra lectures in the world, right? And there is a version of that that is democratizing, right? Students who couldn't before go to MIT have access to MIT's, right, graduate student courses, right? That is very democratizing, but it's not Jim's sense of democratizing necessarily. He wasn't meaning that everyone gets access to the same lectures. He was saying that people get a new way into the mathematics that helps all students, based on their intuitions, more deeply understand the math. So in the beginning research of democratization, and this is my version, maybe Walter will tell us his version, which is probably more accurate later, right? There was really a focus in the mathematics of change and variation. And Jim had this idea of why we're looking at algebra for all, right? And maybe that's a fine thing, but should we really be looking at calculus for all, right? Because this mathematics of change and variation is really important and foundational to both math and science that we're experiencing today. And really, should we be teaching the foundations of calculus from the early grades? Students can make sense of change. They can make sense of motion, right? Shouldn't we be teaching this from the earliest grades? And not thinking of calculus as a terminal course, but as a field of study. It is something that you can engage in from earliest days all the way through, and have that as kind of really a foundational idea in mathematics. And in this work, Jim and others, including Jeremy Rochelle, who's been a colleague of mine at SRI, and Steve Hagedis and Walter and others, they engaged in small design studies at first, and it resulted in SimCalc Math Worlds, and that's been a really, influential and foundational event for many of us. Some of the key things they found there was that students really do engage in interval analysis while thinking of motion, right? Well, first it went fast, then it stopped, then it slowed down, then it went fast again. And that really starts to get us to very, primitive almost ideas of limit theory, but it gets us there of, oh, there's these intervals, and these things are happening in these intervals. And that really is a foundational idea in advanced mathematics and calculus, especially as you make the intervals smaller and smaller. Students have intuitions of speed that can be built upon. A lot, and they're still existing, is this idea that kids have to get rid of their intuitions to understand deep math. Their intuitions get in the way, not that their intuitions can be built upon. And really the work that Jim and others did really helped the field move away from that and look at intuitions as productive things that we can build upon. Not all intuitions are productive, but many are, and we can help students build from those, not have to kind of try to clear their memory and start over, which we know wouldn't work. And some of Jim's ideas were we should really start complex, right, and not simple and build up. So have graphs of really pretty complex graphs of motion, and have students start making sense of those, and not start from the simple and build up. As it turns out, right, that's not where we went. We actually had to take a change off of that one, which I think is a little unfortunate. And he had the early introduction of velocity graphs, and students can count up the area under the curve. And we talked about that a little bit earlier on today, and for reasons I'll discuss, we actually didn't kind of work. Our work deviated from that as well. So that's a little bit of lessons learned of where some of these great ideas meet the constraints of real school, of large-scale schooling. So what does this look like, right? I think it's worth saying a little bit of what do we mean by dynamic representations in the mathematics of change? Well, one representation is narrative, right? Ronaldo started off ahead but was running slowly. Geneva started off behind, but she was running faster and was ahead by the end, right? So that's a story, right? Students can start to understand that story. Well, we have what does that story look like in the motion phenomena, which is really in the middle and grounds a lot of the work, right? It's the motion phenomena that's the grounding of this. Then there's graphs of that motion that has some insights. There's tables that represent the motion and the graphs, and that provides other insights, right? And then there's the algebraic expression, which is the end goal, and it also has their insights. So Jim and we were never saying, let's not get the kids to algebraic expressions. It's let's get them to understand algebraic expressions by starting elsewhere, right? And so sometimes the things are misunderstood and said, oh, so you don't think kids should learn the algebraic expression. Like, no, we do think they should learn the algebraic expressions. We just don't think it's the best, most productive way to get there is to start with those and have those be your primary representation. 1 second. And by doing this, we see this as an opportunity to really help students focus on mathematical reasoning. So in the software and the materials, when we design these materials, right, we design simulations of motion phenomena. We can link representations, the motion simulations, the graphs, the tables, the symbols. Something that's very important about this is they can play, pause, step through, and have an exact replay, right? That's actually quite important that technology gives you. We can say all the children have not only seen the same motion, they can replay the same motion as many times as they want. Often, without this kind of approach, people talk about, well, think of the time you drove to the grocery store. Have these children walk across the classroom. Well, you cannot get an exact replay of that. Different people might perceive different things, might focus on different things, and it's hard to get everyone to kind of converge and focus on the same things and point out the same aspects of it. If you can play something that you know is the exact thing multiple times, we can have different perspectives, different interpretations come together, but still all bring them together and then replay and review and see, are these actually different opinions, or the same, or are they just looking at different aspects of the graph? Is this something we have to go deeper on and say, is there a disagreement here? Or it's like, oh, you're noticing this, you're noticing this. Can they both actually be true? And again, that's very hard in a non-technology environment. And we get things like, in our materials, there's multiple function capabilities like piecewise linear, right? Which means that students can get access to kind of reasonably complex motions that they can still understand, that builds on their intuitions of interval analysis. And then when we see it enacted, when it's enacted well, right, we find that simulations of motions ground the conversation of things I said, right? These simulations of motion, they can relate it to their existing real-world experiences, but also see what's different, what's the same about their real-world experiences or what they're noticing. You know, so I have seen children look at a motion that they intended to be fast. They actually created a motion that was very slow and just start laughing and say, oh my God, my grandmother could run faster than that, right? And then other kids talk about things, right? And so it really does, it's rare in math class that there's like joyous laughter that's related to the mathematical topics at hand, but we can get that when we do this kind of activity. The graphs of motion and the tables provide easier entry than the symbols, and that says to motion, it should be to the mathematics, than the symbols. The narrative and storytelling scaffold and support student understanding of mathematics, right? And it's in these telling of stories that the students can actually learn the math. They're not an aside, they're key to understanding the math, right? And when we do this, more students can participate in the conversation than in traditional ways. We're not just looking, and those that understand or are brave enough to actually state that they don't understand something about the symbols and ask questions. They're not the only ones engaged, right? All students can engage in some way when we're telling a story about motion of what happened on that trip, right? So really the focus on a deep understanding of important math, right? So what's the impact? Well, the initial impact was we had some boutique studies where a few people ran classes and created materials and found that what young, underserved students did was well beyond what people thought possible. It was really, you know, the research that came out of this really was astonishing in that young children could do really incredibly deep mathematical thinking, and people didn't expect that it was even possible at all. So that had really amazing impact and influence throughout education. I have the but, ... I forget what's going to come next. I could say but when people go to their elementary school and middle school classrooms now that their kids are in, they do research in, they don't see things like SimCalc, right, ruling the nest, right? That's not what people are doing right now. So somehow we kind of miss the impact at scale, right? And so what does that mean? How do we get into that impact at scale? Well, we found the activities were difficult for teachers to use. Teachers were not raised thinking about mathematics this way. They didn't go to school for, you know, they didn't get their teaching degree thinking about mathematics this way. It was really very difficult for them to do. Especially when looking at elementary school, the math we're talking about is well beyond elementary school teachers' mathematical knowledge, right? I mean, it really requires a very deep understanding of the mathematics. And some teachers were frankly, you know, intimidated by the math, but they simply weren't trained to do this type of mathematical thinking. And the standards and assessments drive much of education. They drive it on a large scale, right? When a district's goal for democratization means underserved students should do better on the tests, right? That's not always 100% consistent with our underserved students should learn more deeper, more conceptual mathematics, right? And so that's been a really, well, it's just been a conflict for us for much of the work that we do. Right. So the next step after that small, again, that was a very, you know, that was like, I don't know, 10 or 15 years of research in like 7 minutes or whatever, right? But then the next step was, well, let's integrate curriculum, technology, professional development, all with local standards. Let's align it to local standards, right? And so this is the logic model that we had for a large-scale randomized controlled trial back about 10 years ago or something, where we said, well, we'll have software and written curriculum and professional development, right, that will be part of, will go into this kind of environment where the student, teachers, and the content are interacting with the goal of more and deeper mathematics learning for teachers and students. Right, so and it's aligned with local standards. That's the interesting part. That's the different part here. Right, and in particular, we asked the research question, can a wide variety of teachers use an integration of technology, curriculum, and professional development to increase student learning of complex and conceptually difficult mathematics? Right, so that's key. Can a wide variety of teachers use this? So it wasn't us going in, it wasn't us and our 5 favorite teachers. Right, can a wide variety of teachers do this? For this study, we went to Texas, which at the time, and this was pre-Common Core, they provided a great test bed for scaling research. They had a statewide aligned system of standards. They had people delivering high-quality professional development that we knew that we were colleagues with. They have and had a very diverse student population. They had, and probably still have, a mechanism in place where we could work with local PD providers, right, and find teachers that would be interested in this study, and they would be able to support the study. And we had a partner in the Charles A. Dana Center at UT Austin, very high quality group that was very well aligned with what we did, with what we were thinking of. And we were able to find students from a wide variety of locations. We had students from rural areas, students from the border area down in El Paso, which is, I believe at the time, was the most impoverished county in the nation. We had students in the capital city of Austin, in the metropolitan area of Fort Worth. So we could really look at a wide variety of teachers and a wide variety of students. And we chose to focus on middle school math. And as I said before, I led off talking about how Jim was going earlier and earlier grades. And we found that if we wanted to be aligned with the standards, then then middle school math was the place that made the most sense for us. And again, and aligned with middle school standards, not with kind of some of Jim's original ideas of velocity graphs and getting to calculus and area under the curve, but much more around rate, proportionality, and linear function. And so we started with 7th grade. At the time, the testing there was lower stakes. And as I said, we were looking at rate and proportionality. And then we scaled to the 8th grade with a focus on linear function. And we used a replacement units model. So we had each replacement unit, 7th grade and 8th grade, was 3 weeks long. And the teachers chose when they wanted to implement these units. They were recruited, they were randomly assigned to treatment or control. And they told us when they taught the relevant standard, and we gave a pre-test and post-test surrounding that time. So it was different teachers at different times of the year, especially depending on their district and their pacing guides, taught the unit. But there was a pre-test and a post-test right before and right after they taught that, the related units, either treatment or control. Not that this is that important, it's just looks at how we looked at the standards at the time, and again, this was pre-Common Core, so the Texas had their own standards that were pretty close to the NCTM focal points, and people may remember the good old days of the NCTM focal points. They were well aligned in some ways with what we wanted to do, and were really a precursor of the Common Core, and there was, of course, a great research literature base. Right, so we didn't come out of this out of nowhere. We came out of this making sure we aligned the research literature with the overarching NCTM focal points, was the closest thing to national standards at the time, with the local standards. That was also important to our work. We co-designed 2 curriculum units, as I said, the proportionality in 7th grade, and that was typically, well not typically, that looked at linear function in the form y equals kx, and then linear function, which is the form equals y equals mx plus b. As in not that relevant aside, interestingly enough, if at the time you said y equals mx in 7th grade, you would be told by many people you were wrong, that's y equals kx. So there was a little bit of people hanging very closely to, even as we were trying to move away from symbols, there was definitely some people holding very tightly to the symbols in a way that wasn't even necessarily appropriate. So we had professional development. That professional development focused on not only the math, but the technology and the written materials. And so this is a picture of one of our PD sessions where the teachers had their SimCalc units up, they were running them. We actually have our teachers go through our units for at least part of the professional development. And we think that's really important, having the teachers work through as learners. As I think I'll mention later, there's a lot of constraints on teachers and districts' time for professional development. And in a way that's really too bad, because while teachers could go through our units, much more quickly than students, it really does make sense. We believe it makes sense to go through the entire unit, because often teachers say, no, you can't do that. They don't know this yet. But when they go through the unit and say, oh, now I understand. They're asking about this, and then you introduce this, and I see how it goes through. And when they're just kind of introduced to pieces of the unit at a time, they'll often kind of do their own reordering of the unit, because they don't have a full understanding, right, a full appreciation for how the unit kind of builds up on ideas, and is a nice kind of progression through the materials. Now we also needed assessment items, and we did not use the end-of-year Texas State assessment. We worked with a group of assessment developers to create an assessment that had 2 types of items. It had what we call relatively simple items. They're kind of traditional items in rate and proportionality. So you see here, a car of the future will be able to travel 8 miles in 2 minutes. How far can it travel in 5 minutes? And that's a classic, you give 3 and ask them to find the 1, right? And however you want to do it, right? And that's a classic proportionality test question. Versus what we consider a more complex question, right? Here's 2 graphs. one of these two objects traveling the same speed. So it requires comparison across functions. It requires you kind of understanding that slope is speed and finding out where the slope of the two graphs are the same, right? So that's really about a relationship between two functions, right? Also in the simple proportionality, we could have reading a specific value in a graph or a table, or reading one value in a graph or a table, versus in complex, we often have them make comparisons across representations, right? And we very cleverly call the simple ones M1 for math 1 and the complex M2. So when you see a graph like this, you see in the bottom M1 and M2. The M1 is the simple math and the M2 is the more complex math. We worked with a lot of vocabulary and we had debates about every one of them. So in the 7th grade, we see the graph on the far left that the leftmost bar are the control teachers, and this is a pre to post test gain. So we're given the same assessment before the unit, after the unit, right? And then we subtracted, right, to find their gain, right? And what we see is that, well, the first graph, to let you all know, says year 1 experiment. That was 7th grade, first year treatment control, right? The quasi-experiment was those that were in the control group, right, then were given the materials the second year, right? So it was really a delayed treatment, not a pure treatment control. It was a delayed treatment. So that compares the same teachers. First year they did not use the SimCalc materials. The second year they did use the SimCalc materials with the same assessment. And then the third graph is the 8th grade, where we only did that in the second year, right? So we see across all, students did about the same on the M1, the simple math questions. There really wasn't a gain there. Where we found a really large gain was in our M2 items, our kind of more conceptual items. And we had a large effect size with that. So that was something that we were really excited to see, and we saw that, okay, students didn't do worse on the test of basic math items, right, which is possible, right? If you spend all this time on your more advanced, more conceptual math, are they going to do worse on their basic calculational math, right? And we see that and these students and a large number of teachers were able to use our materials, right, to help students make large gains in conceptual mathematics. So we wanted to look a little bit more closely, and I'll look a bit more closely again, where here we see that gender, male, female, there was really no difference. For ethnicity, we had the students in, oh, and that's interesting, it says Cornerstone. Sorry about that. Pretend it says SimCalc. That we had the material, our materials led to greater learning than the control materials, and based on poverty level, right? So this really wasn't like one set of students was really driving this, right? We found across a large number of demographics, students were able to learn more conceptual math. And I want to say these are gain scores, so we're not saying that at the end all students, right, perform the same. We're saying all students learn the same, right? Or learn more compared to the control materials. Okay, so then, right, mission accomplished, right? We saw a wide variety of teachers could use it and we're fine, right? But we did see that use did drop over time. Some, and even at first many continued to use SimCalc, but also many did not. And then as time went on, other units came in and displaced SimCalc. Teachers expressed concern about the time required to use the materials. Many teachers were just concerned about alignment with the state test. This is our own assessment. We didn't say anything about the state test that they're actually responsible for, right? And we went out and we talked to individual teachers at individual schools. So we did not have school level or district level personnel involved. So we didn't have champions at the district to bring this forward and say, this is what we want in the districts. This should be moving forward, right? And so while we had a reasonably large number of teachers use it the first year after the study, that number kind of kept dropping and we didn't have any way to kind of regain momentum, right? So our next steps were we wanted to do more scaling studies. And it turned out we had opportunities to do those in Florida and England. And we also wanted to work a bit more on our model of scaling, right? What does it mean? Like, we showed that teachers could use this, but what does it mean to then try to use this and scale it? So when we designed for scaling, we adopted what's called the curricular activity systems approach. And so it starts with the same triangle in the middle that we saw and we've seen before, right? We have the teacher, we have the students, we have the content, including our technology and our workbook materials. And we know that students come in with their existing experiences, existing knowledge, their needs for learning. Teachers come in, they have their own, their teaching moves they're most familiar with, that they're most comfortable with, their own math knowledge, their own beliefs and attitudes. And the content is both the written materials and the technology. So if nothing else, you have to take all that into account, right? We can't just put it out there and expect people are going to use it the way we intended. But perhaps as importantly, or as importantly for scaling, there is a very complex environment they're working in, right? The adopted standards that they're using are very, very important to teachers. Teacher evaluations were becoming important. Right now, they've become even more important. Right, we've had this slide for a long time, and teacher evaluation should be getting like bigger and bigger or something, because right now there's these large teacher evaluation efforts, and depending on the checklist the district administrator, the principal's coming in with, what they're doing in our materials may or may not align with what gets you good marks on your checklist, right? There's accountability demands that have just simply been growing and increasing. There's professional development. How much do you get? How much don't you get? What's supposed to happen? How much of your professional development is already accounted for, right, in district mandated time? And then we have school and district goals, right? And those goals, maybe we want all of our students to learn deeper mathematics or deeper STEM, but they may also be, we want our students to perform better on our assessments. Right, so we realize we have to take all of these things into account if we really want to both have impact in the classroom and scale our use. So to do that, we created some strong local partnerships. We really thought working on the partnership level was very important. So in Florida, we worked with a local trusted university partner, University of South Florida, St. Petersburg, and we got strong buy-in from a district supervisor that university worked very closely with and worked with. In England, we worked with a local trusted university partner at the University of London, and in particular it was Richard Noss and Celia Hoyles, who at a large meeting in front of some bunch of people accidentally called them Professor Noyles, which is the greatest thing. We got approval from England's education ministry, right? Through the funding mechanism, they actually had contact. So the England's education ministry saw what we were doing and was able to kind of give their kind of stamp of approval. And we hired respected curriculum consultants and coaches to work with us to ensure that our materials made sense for what they were teaching and when they were teaching it and the way they were approaching the materials, right? So we modified our existing materials. In Florida, we actually changed our name from SimCalc to SunBay Digital Mathematics, and that was in part because we were not only using our SimCalc materials, but we're using dynamic geometry materials. We started using GeoGebra. That was looking into Geometry Sketchpad, and we really felt that the name SimCalc was getting used to mean many things. It was a particular software package. It was also a research agenda, and we wanted there to be a name for this project in particular in Florida. Also, for those of you running studies with large numbers of people where you don't know all the teachers' names personally, having a logo, while seemingly trivial, is actually kind of important, because you want every communication with them to have your logo on it really big so they know it's from you and not junk mail or someone trying to sell them something else. Just for students who may go out there in the world with big projects. It's actually kind of important. And in England, we were named Cornerstone Maths. In part, the folks in England didn't really like SunBay math. Like Cornerstone it's good and hefty, and they don't have very much sun there, and so it was like, that name doesn't make sense. And it seems weird that these were very related projects, but also made sense for us. We needed to know, we were talking about the Cornerstone teachers or the SunBay teachers, talking about the Cornerstone professional development or the SunBay professional development. So there are times when having these different names, SimCalc, SunBay, Cornerstone, is kind of crazy making, but there are times when it's really important that we do. And in England, they felt the 8th grade motion unit was most aligned with what they do. They felt the 7th grade wasn't quite there. It wasn't a single unit of study the way we had it. It was kind of the way they taught the material was kind of more spread out. But the 8th grade unit they felt was really dead aligned with the kinds of math they wanted their kids to be learning and the type of way they were teaching it. We also created a patterns unit and a geometry unit. We had to align to some British standards and conventions. You know, some of it was the silly stuff of change truck to lorry. But other of it was also perhaps silly, but for instance, they, at least at the time, did not use the word slope until what we'd call high school. They used the term gradient, right? So there were some, and there were a few other minor differences along the way. So we had to make sure it felt British, right? It came in feeling very American. And in Cornerstone Maths, we got the opportunity to move to a web-based environment. So we actually weren't using SimCalc anymore. We were using materials highly influenced by SimCalc, looked very much like SimCalc. They weren't the exact same for many reasons, and I'll show that a bit later. But they weren't the SimCalc materials proper. So we did that. We ran the professional development. We had our close relationships. And I'll put quotes in replicated the learning gains, because it's hard to call these exact replication studies. But this is in Florida, right? So in Florida, we see the blue are the results from the Texas studies, and the orange are the results from the Florida studies. And we see that in terms of the broad replication of gains on the left, that was almost an exact replication. The graph on the right is a little bit hard to understand, but is really exciting to us. It's really interesting to us. So the blue bars are the Texas SimCalc schools. The orange bars are the Florida SunBay schools. And the white bars are the control schools. Each bar is a teacher's gain score. Right? So we aggregated the gain score of each classroom, right, and gave them, and they had a value, what was their gain score, and they got a bar, right? So they were put on this and other sorted, right? So we see that, well, the first thing to look at is when you look at the far right, we see most of the large gains, and depending on what you count as the large gains, right, from here over, right, we see far, far more of the SunBay and SimCalc teachers had large gains, with a small number of teachers were spread in there. Right? So one thing that shows us is our assessment did let those tiny number of miracle teachers really shine, and they were able to really teach their students this deep mathematics, and that's great. And it's about, I think I counted once, I think it's about 1 out of 10, which I think many of our intuitions have. About 1 out of every 10 teachers is that miracle teacher you pray your kid gets, but they have a 1 out of 10 chance of getting them. Right? So we had far more teachers acting like those miracle teachers. Down here, we're going to realize it goes negative, and sometimes people focus not. The negative is -1, right? So really, what that means is there wasn't the learning that we'd like to see. That's statistical noise, right? It's not that the teachers, we're not going to claim that the teachers did damage to any students, but they didn't learn a lot anyway, right? We're pretty sure about that. And we'll see here that, right, it takes a while before we find any of our teachers, right? And so really, we were able to push far more teachers off to the right to get higher learning gains.
And those are number of items?
Those are,
that percent?
Yeah, no, that's number. Yeah, that's total gain number of items. Now, these graphs are going to look a bit different because they're the 8th grade materials that we used in England, right? But we see, again, very similar patterns, right? We see that, in fact, in this case, it's not statistically significant difference, right? There are fewer there, so we see that we have a higher error bar, right? But again, we kind of, to some extent, replicated the learning gains, and we see here, now there were some more of ours over here, but also far more of our Texas and Cornerstone teachers over here. So again, this idea that our gains aren't focused on a small number of students, a particular demographic of students, or a particular small number of teachers. They really help many, many teachers have their students learn much more deeply conceptual mathematics. Okay, so now we can say mission accomplished, right? We did it, right? We showed this across multiple states, multiple countries, but still in Florida, right? We had some ardent users, right? Others saw the value, but like, it's a lot of effort for a couple of units. You know, I have to like bust out the technology, I have to change my teaching style. There's a lot going on there. And it takes a long time, and no one's telling me how my kids are doing on the state tests. It's still not aligned with the state tests, right? So the assessments were seen as valuable, reasonable. No teacher ever complained about it, and they looked and said, yes, my kid should know this, right? This is a good assessment. But it was not the state assessment. In England, the teachers were more enthusiastic about it, right? There, and again, at the time, this is a while ago, their students were not tested yearly. So they said, yeah, this takes more time. Yeah, so the teachers in the United States always complain about it taking more time, or even some would volunteer. Yeah, this takes more time. So, but my students are not going to take their assessment till 2 years out from now. And I know next year I'm going to spend less time. I spend a week and a half reviewing this stuff every year. Right? I'm not going to have to do that. And then teachers were in the for multiple years said, I was right. I didn't have to review it at all. They remembered it. Right? So because their testing pressures were different, they really felt more buy-in and they felt it was more aligned. Right? These materials developed originally for Texas ended up being more aligned with kind of some of the philosophies in England, right, than our original audience. And it also had a bit of a closer alignment with classroom expectations. They really kind of dug more into the students engaging in mathematical practices more than the teachers we've been working with here did. So, in Florida, right, we did not have evidence on increasing state test scores, or at least even not decreasing state test scores, or we have no evidence on state test scores. In the district we were in, the district superintendent was replaced, and of course the new superintendent wants change. We ended up not continuing that district partnership, but we did keep a strong partnership with our university partner, and others in the district who went and got other positions have been strong SunBay advocates, and so I'll come back to them in a minute. In England, teachers did continue to use and scale our materials. They, without us, developed what they called a hub model, where in England there were already these kind of networks of schools that were kind of, they were like professional learning communities. I don't know if we'd exactly describe them as professional learning communities technically. And so then the teachers that use SimCalc started running their hubs, or Cornerstone, and using Cornerstone there. Right, and it picked up enough that it's right now, there's something called the London Grid for Learning. And if you search on the London Grid for Learning, we are a case study still after several years of use that they've picked it up. They're actually scaling it and using it. And in fact, I think it was last year, is it British Educational Technology, BETT Awards. We were actually nominated for a BETT award, and if you look for BETT it's a British Educational Technology something.
Mumble the last word.
Yeah, exactly. And so really, interestingly enough to us, that we've really had more traction there than here for multiple reasons. And Richard and Celia, as well as their colleague Allison, are still actively conducting research and publishing on it. So it's still, got legs there. So the next stage for us is, okay, one of the things teachers were concerned about really is, it's a lot of effort for a unit in A grade, right? We want to make sure that our professional development materials are accessible to even wider range of teachers. There were some minor things like, the technology is difficult to use. But the real big thing was, can we show large-scale impact on state assessments, right? So we did take seriously more units and more grades. So now we have 2 units in each middle school grade, right? The same kind of model, about 3 weeks of use, right? We maintain our focus on foundational, difficult-to-learn ideas, right? We upgraded the professionalism in some ways, like we include these context-setting videos, and I showed some of the students that were here before, at least one of those videos, what they look like. We upgraded our technology to run in HTML5. It runs on most platforms. And so now we have a 6th grade ratio unit and a 6th grade expression unit, a 7th grade proportionality unit, and a 7th grade algebraic expressions unit, 8th grade linear function unit, and an 8th grade geometric transformation unit. So now I can demo this a little bit. I know you guys have those things out there. I should have even mentioned that earlier. I don't know. Well, if people want to go to sunbaymath.com on their devices they've got, or if you can go there, they might even be there. And the teacher ID, it's going to ask you for a teacher ID, and it's capit. Yes. And then the login code is 3548, and someone else is going to have to remember that because I'm about to leave this. And this is really, let me get back over here.
Teacher ID and login code.
Teacher ID is capit.
Yeah.
And login code is 3548. And then it's going to give you a list of students, and just choose any 1 or 2 students, student 1, and just hit next. Right. And then you should get to a screen that looks something like this, right? And this is actually running live, so we'll see what really happens.
SunBay math.
Right, and so these are our units. right? This is how you get to our units in the technology. An important thing, actually, let me, so we're gonna look at the technology for a little bit. It's really important to say the technology is the more fun thing to demo and for people to look at. But each one of these comes with an entire kind of specified unit. So this is the teacher guide to the true colors ratio unit, right? And so we have preface materials that explain SunBay, we explain the learning goals, we explain some of our routines that I'll talk about a bit later, or we talk about different activity structures. Teachers are told common student misconceptions.
What was the cap it?
We're way behind you on the code.
Capital K.
And the code is 3548.
Thank you.
Then just pick any one student, just pick a student and say next. You don't have to do anything more than that.
No, you're right. No, you're right. Wow.
Right, so each of these units has an associated teacher's guide, associated student workbooks, right? And so the technology really is meant to be part of a curriculum unit. So if you go into any given unit, oh, now it logged me out. Let's see what's gonna happen. Right. You'll see a series of investigations, and in each investigation there are a series of activities.
3, 4, 5, 3, 4, 5, 8.
And so each of these activities is made to be pre-set up for the activity the students are about to engage in. So in that way, it's very different than SimCalc. Right? SimCalc is more of an open-ended micro world where you could save documents and then open the documents. Right? Here, there's no such thing as the open-ended kind of sandbox SimCalc. You can only get access to materials set up for a learning activity. We're interested in moving in a sandboxy kind of way, but for now, for the work that we've been doing, all the activities are designed based on our own, all the technology activities are based on our own activity. So here I'm going to show you a little bit of our ratio unit. Right, so again, the folks that were here a bit earlier have seen this before. So what we say is, our conceit for this is you're working for a mural company that's reproducing famous paintings. So you have to make large amounts, or sometimes small amounts, of different colors of paint. Right? So in this, we have show artwork and say, okay, so you're supposed to make that color orange. As it turns out, it's not really important if you make that color orange. Right? And we'll start off with, say, 2 yellow and 3 red. Right, so we see we've got the yellow and red out in this canvas area, right, as dots, right, pips we call them. Right, we have the 2 to 3, so we use the mathematical representation down here. Right, we have a spectrum bar, right, which shows where we are in the spectrum of colors from pure yellow to pure orange. And we see that we have 1, 2 yellow and 1, 2, 3, right, so we have 5 equal size bars. 2 of them are yellow, 3 of them are red. So we have multiple representations of what's going on the screen right now. We can say to kids, okay, well, let's make more of this paint. Pretend you have four yellow pips and you want to make the same color paint. How would you do that? Well, they can add a new one. Right, and I misspelled it, but that's okay. And say, well, we have 4. The first one was 2 to 3, so I have to add 2 to each. Right, so I should say 4 and 5. Notice I could press, so I could enter. Right? Say, huh. Well, now just looking at things, right, this doesn't quite seem right. Right? We notice the spectrum bar moves out with a design choice instead of hopping, but that's important for us now. So this has 1, 2, 3, 4, 1, 2, 3, 4, 5. If you count them out, that's 9 equal size bars. And for some crazy reason, although I added 2 to each, which completely makes sense, right, I'm not getting the same, it doesn't seem like I'm getting the same color. How could that be? Some other kids say, well, I'm not sure you should add 2 to each, right? 2 is doubling this. Maybe we should double each, right? Would that work? Okay, well, let's try that. So this is going to be 4, and this would be 6. Maybe that'll work. Right, like, well now when I move back and forth, that spectrum bar doesn't move at all. Right? I've got 1, 2 where I've got 1. I've got 1, 2 where I've got 1. I've got 1, 2. Maybe there's something to that. Now we also provide this other bar called the container. Right? And we can move our container around. Right? Let's move it like that. We have 2 yellow and 3 reds. What happens if I take this and put them in the container? Well, I have 2 yellow and 3 reds, and 2 yellow and 2 reds. Well, that's weird, right? And it's not even, and it's aesthetically unpleasing to me, right? But there's nothing I can do about it. I can't make it aesthetically pleasing, right? But when you go here, what do we have? I have 2 yellow and 3 reds, and 2 yellows and 3 reds. In fact, it is doubled the other thing. Does it have to be doubled? Right? Suppose I keep doing 2 yellows and 3 reds. Well, that would mean 2 more yellows. That would be 6 and 9. Would that work? Right? Well, let me get this one. I'm not happy with this one. Here, let me just move that out of the way. Well, but then that happens. And let me put this last guy in a container. It's going to be all over the place, right? And I get 2 yellows and 3 reds each time, right? So what's important about this, and we think has some similarities with the SimCalc way of viewing things, is that we didn't have to logic kids out of an additive model being incorrect and try to harangue them into believing that it should be multiplicative, right? You're actually using your intuitions, your senses, your understanding of color, right? And saying that that's not right. And just like in SimCalc, I'd say, SimCalc does not do a great job of explaining slope, right? It's the teacher that explains slope. It's the kids discussing what's going on in the motion, figuring out the motion, figuring out the speed, where you come to an understanding of slope. This is not teaching you, right, ratio and proportionality. This is giving you the experiences to try to explain to your students, to try to talk to the teachers, try to engage in activities where the key mathematical understandings will become emergent and they make sense to you, right, when we get into the mathematical discussion. So we're not giving you a definition and having you practice it. We're giving you problems and things to think about, right, that then when you engage in mathematical discussion, the understandings kind of arise more naturally. Very quickly, just to show people, you may all be familiar with SimCalc. So this is our not quite SimCalc, but highly SimCalc version, right? So we could say, you know, make a race in which the blue runner will win. Say, okay, well here clearly the blue runner will win because I'm looking at this and I see that that blue runner's line is longer. They go out further. So clearly the blue runner has to win. And see, as in SimCalc, we see the line grays in as they go. We see that we have a clock, we have a data table. We see, like I said, it's not full SimCalc. We don't have everything it has. We've made a few other design choices. And we see that the blue runner did not win. Right? That's weird because the blue runner's line is bigger. They seem to be going out further. What's going on with the blue runner did not win? Right? I say, well, okay. Let me go like this. I'm going to make that blue runner. Maybe that'll make the blue runner win. Right? And boof. Okay, now we've got the blue runner winning. That's kind of ridiculous. Like, can anyone run that fast? And kids will laugh about it when they see it. Right? What happened there? And they'll play it again. Like, wow, how fast is that? Right? And they went, what did they do? They went 108.89. Well, let's make that a better number. Let's make it 100. Right? And so through this way, we have students engaging in their own. Again, they're engaging with mathematical objects quite directly. They're engaging with their intuitions of speed. And they themselves have the question of how can we decide how fast this runner is going? Right? So I'll just do one more. Right? And this one was less actually successful than others. When we talk about expressions and variables, something that we know from the research is that students have a very hard time with equivalent expressions, and especially with the idea that variables might vary. right? They tend to look at variables as unknowns, not as things that can actually vary. So we've made this environment. We say, okay, well, let's say this is x plus 3. Let's make 3 plus x, right? And now I have two expressions. We see we have 3, and we have an x bar here. And addition is by stacking, right? And height is value. And we have x, and we have a 3. And we see if we turn on our evaluation line, they both come across to 8, right? Well, does that mean that 3 plus 5 is equivalent to those, right? Because when we turn our expression on and on there, all evaluate to 8, right? But one thing we can do in this environment, right, is we can say, well, if we say x is a variable, let's actually vary it, right? And what does that mean? And oh, well, we see this 3 is anchored to the bottom. That 3 is not anchored, right? So talk about variant, invariant. That 3 is not anchored, it's moving, but neither one of them changes, right, their relative height. Where those x's do, as I move this up and down, wait, and as I can even play it, right, I get the sense that no matter what values of x, right? Now again, we're not showing all values of x, just like in dynamic geometry, when we drag through, we don't show all possible values. We show those ones that we're showing, but we get this idea that, right, through many values of x, these two remain the same. That guy with two constants, right, doesn't. That stays anchored, right? So it's through some of these ways that we're trying to build students' intuitions in ways that are really hard in non-technology. One thing I want to point out before going forward, the ratio and the SimCalc-based units, right, are really, by most metrics, quite successful. Teachers like them, students like them, we have high use. These particularly have 2 units using this. They're actually less successful. And these were the most kind of controversial as we were building them, right? They don't have a clear real-world-ish simulation, right? The ratio, they were trying to build colors. They were trying to make more of a color. Here we were saying, well, is our representation and simulation kind of the same, right? And we really found that they were not. People tend to not move so much. They tend to just hit the evaluation button and see what they evaluated to. They get kind of the things that you can almost do on paper. So anyway, just as a little caveat to ourselves, right, is that to some extent we didn't fully engage in all of our own design principles, and it actually showed. So there's something to be said for keep to your design principles, if nothing else. Okay, so now I'm going to carry on. Okay, so that was a little detour to say, you know, what are these materials, right? Just to go back a bit, we talked about our units, we talked about moving on in Florida, what's next, and so when we made these units, these are what these units look like. And the assessments problem, right? I keep coming back to this assessments problem. Well, the good news is this was a sample park assessment item. Before, again, it was before park was being used. And this is the kind of item you should expect. You have object A and object B, both in graph form. Object C and object D, time and distance. It looks shockingly like ours and put from greatest speed to least speed. In fact, when you look at something from our SunBay curriculum, before we ever saw this, we had, here's a graph, make a table, here's a graph, make a table. We also had them put in the equation and then write about which is faster and why it's faster. So we looked at this and said, okay, right, now we're cooking, right? And Florida was leading the park consortium where we already had strong relationships, right? So, okay, we've got our chance to go in. So we proposed to the Department of Education investing in education competition for a randomized controlled trial for a validation study. We recruited 2 large districts in Florida, and then we also worked with the University of Florida that had a really close partnership with those districts, and we randomly assigned 30 treatment schools and 30 control schools. And these are large schools in large districts, right? So this is a large number of teachers and schools. We also engaged simultaneously in a design study in one small district in Florida, where we kept our close partnership with USFSP, and USFSP knew that district And from the prior district, some people there had left and come to this new district, so already SunBay fans. So we already had a close in, right? And so that we wanted to have a district we could work very closely with, do more design work, not have to have this kind of, as you might know, if you do a randomized controlled trial, you can't mess with the treatment too much. You have to have a consistent treatment, right? But we could mess with things more in our design study, try to do more experimental things. And in that case, they were not randomly assigned at all. Some teachers in each school were kind of voluntold to be part of our project. They could bow out, some did, right? Most stayed in, but it wasn't this, you will do this. It was like, principal would say, hey, I think you'd be a great teacher for this. It's a new initiative, and we want you to pilot it in our school. Not, you've been told to do this. You can say, I might be coming back to that. In the study, we worked with over 300 teachers and over 30,000 students a year. So, you know, when we talk about a wide variety of teachers using a wide variety of students, I think that counts, right? So the study design in the randomized controlled trial, year one was a pilot year with, we were only in 6th and 7th grade, right? We wanted to collect baseline teacher and student data. We collected feedback from teachers, and it was just too much, even for the schools, to roll out to all the middle school math teachers in 1 year, right? So the districts even pushed back on that. And then year two was our evaluation year, where we rolled out our 8th grade materials, and we did actually, you know, that was the year that we did the formal data collection and analysis. And year three was our sustainability year, them to try to ramp up the use, especially to the schools that did not have access to our materials or were held from access from our materials for the first 2 years. In our design study, we had design and iteration years, and in year three, a sustainability year. And for all, between year one and year two, we're able to do a significant amount of iterations. Like I said, in a randomized controlled trial, your treatment has to be your treatment. But year one was always a pilot, so as long as we maintained our treatment consistent in year two, right, it didn't have to look exactly like year one. So we took that opportunity to further refine our materials for this audience. The context of our study was when, by the time we got funded, complete upheaval. Florida had left the park consortium. They called it federal overreach, although they're the ones leading the consortium when we submitted the proposal. They were using a new assessment that was both developed and piloted in year one of our study. It did not look like the park assessment. It was definitely a bit more traditional. They had new textbooks. I was actually doing some classroom observations when a guy came in with a pallet into the classroom of the textbooks they would be using for that year. We're already about a month into the school year, right? And there were new PD initiatives in the districts. They had to learn the new standards. They had these new textbooks. And parents were concerned both about the amount of assessment and about the amount of time teachers were out of the classroom doing things like getting professional development. So there were initiatives of minimizing the amount of out-of-class professional development teachers could go to. So that's where kind of a bit of reality set into our beautifully laid out proposal plans, right? Now the good news is we did have very close partnerships, right? And one of the things that meant was we really attended very closely to district documents. We knew their standards, we knew their assessment blueprints, we worked with them on their pacing guides, we were working with them on their existing curriculum. Like, we knew the math curriculum, the math curriculum supervisors very well in this project, right? And we actually recruited people within the district to deliver the professional development and to work with us on refining the materials. So we were well embedded in the district. Right, so like I said, we involved district math coordinators, professional development staff, the local university partners. And we did iterate significantly between year one and year two. And an important aspect was we had to learn exactly where we could compromise and where it didn't make sense to compromise. Right, so I'm going to tell you guys a little bit about some of these compromises, like what they look like. One, so this is a page out of one of our teacher guides, right? And it looks like a regular, you know, this is a page, this is an overview of what your day is going to look like. We did not warm-ups, and the problem solving is really homework. We didn't want warm-ups nor homeworks, right? But teachers said, my kids come in, I have to take attendance, I have to do these things, I have to collect assignments, I have to collect field trip forms, whatever it is, right? I need my warm-up time. And if you don't give me them, I'm going to make them up. And we saw in year one teachers making them up. We said, okay, we'll give them to you, right? And so what we did was we had the warm-ups could not have student collaboration. Our first set of warm-ups involved student collaboration. I said, no, it has to be quiet time, but I have to take my attendance, it has to be quiet, kids will be working alone. So we had the warm-ups be very fast, They're supposed to be about 5 minutes, and it was students practicing the math procedures that they would be using in order to solve the problems, right? So if it was a question where someone was running 2.5 meters a second for 12 seconds, one of the math homework assignment, one of the warm-ups was 12 times 2.5, right? So that way they could do it on their own. When they reached the mathematical procedures in our materials, it actually at least thought about it a little bit. So we tried to kind of tune it so it met the teacher's needs while not veering too far from kind of what we wanted. And yeah, and in the homework, right? So what we did with the homework was we always made one problem. We called it the sun problem, got a little sun icon next to it, that we felt was indicative of if the kids really understood it. So we said, if you want homework, here's one, several questions. Make sure they do the sun problem. You have, right? We're fine with just saying, just do the sun problem, and if you have extra time at the end, have them do the sun problem. Have that be the one you talk about, right? Don't start the homework from the beginning and go through the end, as teachers sometimes do, because that's not really what we want. We want to know, did kids, we want you as a teacher to know, did kids understand this particular problem, right? That's core. We also put in far more strict timing guidelines than we thought we'd have to. We thought we'd tell them in professional development and, they'd kind of understand, but the warm-ups would go for 15, 20 minutes if, just naturally, because they want to make sure every kid did all the warm-ups and got them correctly. So we started putting in more strict timing guidelines, and whereas before we were very loose with the classroom structure. We knew some teachers liked having students collaborate most of the time. Some teachers could run very good classes with not much student collaboration, as long as the students were engaged in the talk, right, and in the math talk, right? But teachers really asked, I want to know what to be doing right now. Are the students supposed to be working in groups? Is it supposed to be individual work? Is it supposed to be full class discussion? So again, those you just gave stronger guidance than we really thought appropriate. Where did we not change, right? Well, we have this routine called predict, check, and explain. Right, and students, I didn't say this before in our materials because I knew we'd get to it here. Students were told, teachers knew students should work in pairs or threes at computers or iPads. This is not a one-to-one program. This is a collaborative program. It's explicitly collaborative, right? And students did each have their own workbook, right? And predict, check, explain at least once, typically twice per each lesson. Students would be posed a question. The prediction could be, given this graph, who's going to win the race? Draw a graph that would have this result, right? It could be one of many things, right? And then they would check it by either, sometimes it was just running a simulation we had set, sometimes it was going editing, making a simulation. And then they would explain, and both students would share with each other, what was your prediction? Did what happen, what we expected to happen? If it did, explain what we were doing and why we thought that. If not, what was different, right? That is not I do, we do, you do. Right? And a lot of teachers really kind of are tied to this I do, we do, you do. And that's kind of the opposite, right? It's called the gradual release, right? We did not want teachers to model solving the problem, right? Then with this, and that's what I do, we do, I do, we do, you do means. I do, right? The teacher models solving the problem. Then we as a class go through and model the problem together, and then you all individually do it, right? And so we had the request, well, can you make your activities more like I do, we do, you do? And we say, no. No, then you're not doing SunBay, right? Ours is a very particular method. Similarly, non-negotiable was intuitions before vocabulary. This is a place we could actually get in trouble with some of the teacher performance evaluations where principals and others have on their checklist that teachers should have the vocabulary going to be used written in and defined, as well as straight learning goals on the board. Said, no, the point is not, you don't define slope and then have them do this activity where they're going to investigate the relationship between the steepness of the line and speed, right? That short circuits the thinking, right? It has to give the students an excuse to not do the thinking, right? So that was an area where they no, we are introducing the vocabulary when it's appropriate to introduce the vocabulary, right? So that was another non-negotiable for us. We had some difficult decisions to make in translations for English language learners, right? Exactly how much do we translate and what makes sense to translate, right? If you don't know, if you're not an English speaker, giving you the definition for slope, I'm just going to keep using that as the one definition, in Spanish, might not be helpful if you still haven't learned slope anyway, right? Like then you're learning it in Spanish and English, right? There was some debate amongst our team and English language learner researchers about what's the most appropriate thing to do. But we did realize some children were just simply not getting access to the materials because we talked about a race, right? We talked about a road trip, right? We talked about these things that, what are these things? Like I'm being excluded from even the context, and you're talking about the context being important. So we decided to provide translations for all context setting text, but not the mathematical text. And that's still, that's still a controversial, it's still a debatable choice, right? But that's where we came out. So for instance, the videos had an actual, a translated transcript of what's the video, and where we had extended things like so-and-so and so-and-so ran a race. They did for 5 days, that we provide that in translated form, but not the mathematics. So again, that's still something we could do a bit of work on, is how do we make sure that English learners get access to the written materials. I'll talk about, we're also doing some research on, with English language learners, intentionally with English language learners, to say, does our dynamic representation get them deeper access to the material so they can more formally engage in some of the mathematical practices, right? Because you do have this kind of direct access to mathematical objects. So we're going to talk about quantitative results soon. First, just for fun, because it makes me feel better about things, some unsolicited teacher quotes. We're just finishing our 8th grade SunBay unit on functions. This is awesome. My students have a deeper understanding how functions work and how equations, graphs, and tables are related. Thanks, SunBay. And again, these are things that our district people got mailed to them from teachers, and they would just mail on to us, say, hey, just to let you know, this happened. I wanted to give you a testimonial this morning. I was teaching my 7th graders today, and I mentioned proportion. Again, 7th grades, they're talking about referring to the 6th grade. I asked them if they learned proportion last year. They were excited to tell me in detail they learned proportion using SunBay and describing the mixing of colors. They seem to have retained the concept only. We do not know if she used a valid measure to decide if they actually did retain the concept, but it's good they had that impression, right? And she said that this allowed more individual time with students. I assume she meant her own individual time with students on lower level, while allowing those in more on grade level. And so again, it's not really a personalized and adaptive, but I think what she was saying was the students at higher levels could engage with the activities, with the materials, while she spent time with the students that were at a lower level of math understanding by her judgment, right? We also, I'm going to talk mainly about quantitative results, but we also had some really interesting qualitative findings, so a really wide variety of implementation, right? We did find out some teachers spent significant time on homework, warm-ups, and remediation. Some teachers spent significant time on predictions, right? Effectively pre-teaching. Okay, we're going to make this prediction. Your prediction should look like this. You should do this to da-da-da-da-da, and kind of go through the unit, right, in the prediction phase, and only then do the play and the explain, right, the check and explain. And that, again, could kind of short-circuit some of the student thinking. And there were some teachers that really engaged in exemplary teaching. This was the way they were wanting to teach, and we saw some really exciting teaching moments in the small numbers of observations that we're able to do. The time constraint is real. Most teachers did not finish. They didn't finish in a couple ways. There was a drop-off in the last few investigations. We have charts, both from looking at their workbooks and from some of the usage logs, where towards the end it just starts dropping off. Teachers had a difficult time of choosing how to, like I put, catch up if they got behind. But the pacing guides rule, by the way, right? What teachers do, right? The pacing guides kind of rule. And once they started getting behind the pacing guide, some teachers, they didn't know what to do. So some would just go through, like, try to compress 2 activities into one day. Some would skip activities altogether. Some would start putting activities in different order. There was a little bit of, like, okay, I'm getting behind. I'm not quite sure how I recover from this. And, and the time pressure on teachers is intense. I mean, something we heard a lot, right, was, yes, we're complaining about the amount of time SunBay takes, but we complain just as much about the amount of time our regular textbook takes, right? Like, we're just being asked to do too much, right? And SunBay is one example of it, but it's not the only example of it. Right, so, quantitative results for our randomized controlled trial. These were run, by the way, by CPRE out of UPenn, so they did an independent evaluation of us, which was required for the I3 grant. So this is all the data that they collected, and they very cleverly thought to collect data on technological pedagogical content knowledge, or TPAC, as well as a measure I'd never heard of, which is teacher allowance for students struggle with problems. right? And teacher allowance for students struggle with problems. It's a survey measure, right? It's not an observational measure, but a survey measure means you can provide it to all 300 teachers, right, quite easily. And how do teachers feel about students not fully understanding the math at the first go and them having a bit of struggle? So it's really kind of measure on do students buy into this idea of productive struggle, right? It's kind of a crude measure of it. And interestingly, there was and teachers reported an increase in student collaboration in another survey that they had, right? And they also reported an increase in student collaboration after SunBay use, right? So SunBay gave them like an impetus for collaboration, and then there was more, even beyond the use. And all these were statistically significant, so we're really very excited about that. I mean, in this huge RCT, where we statistically significantly increased TPAC, teacher knowledge of student struggle, and teacher willingness for collaboration. The student FCAT results, there was no significant difference between SunBay and control students, right? So there's an interpretation of that that reads as SunBay has no effect on student math learning, right? There's another interpretation of that that says SunBay increases student collaboration, participation in math practices, and conceptual math, all without reducing their scores on tests of basic math, right? So there'll be great debates, right, within our team and throughout about what is a reasonable interpretation. I'm sure there's others, right?
The obvious one is the tests aren't sensitive to instruction.
Yeah, right, and that's the one, and I've sent like 20 people to your...
Who writes the PARC test?
Yeah. Well, it wasn't the PARC test, right? It was the...
So, I mean, I'm sorry. It's just,
Yeah.
because the danger is, I would say, the representation of what's problematic in the second case, that it's about basic math, is common in math. It probably isn't the top. Come back later.
So you're saying it's not even about basic math. It's just about being sensitive to instruction.
I don't want to interrupt your talk. Sorry.
That's
come back
fine.
to it at the end. But there's another interpretation that seems supported by Polikoff and other studies that have attempted to say that there's so little sensitivity to differences in instruction, including things like using software or different approaches, and so that whatever these things are measuring, they're not measuring math context. They have faced with these extraordinary levels of reliability. We just have no idea that they're measuring.
What they're measuring, yeah.
And so the real danger, especially for you all, is just to reduce the notion of a math without losing the score of basic math.
Mm-hmm.
So the classic thing is that the high-stakes tests are only low-level skills. And so they can make the test harder, or they can make them look like higher-level skills. It's a dangerous juxtaposition for you all, because the account of why they're not doing better is not because the math tests are only about basics. I've had this debate with Dick Lesh. It's that they are measuring a non-math construct. And I'm not, there was a time when I was the only person saying this, but that's been backed up by anyone who's attempted to find, like I was waiting for this slide, I don't know why it's sense. Because if you, the early SimCalc stuff and the scaling up stuff was all your own items.
Yeah.
And if you didn't use the high stakes tests. And part of why people might have some concern is, you know, my kids get evaluated on the high stakes tests. It's great that on your own tests, even if they're designed by very competent professionals, it's still your own meter stick in a sense.
Right.
And that the teachers, in trying to decide if they're going to sustain the use, are going to, what helps with this thing that I get evaluated in terms of. And so this is a pretty front and center discussion to have when you try and explain this.
Right. And well, here's the next interesting slide, though, right? So we also had our design study, right? It was not designed for comparison of SunBay versus non-SunBay, right? The district is like, hey, we've been working with you guys for years. What's the impact of SunBay? It was never the goal. The goal was we were doing a design study. So, thing called, actually, I put propensity, a propensity score match and an impact analysis. So a propensity score match is a statistical technique where you find the people in your sample, say those materials, and then you search the district or the similar student who use your material. So you kind of build a post hoc comparison. Look, and interestingly, 6 significant increase in percentile points in end of year set. We had a margin of percentile points in progress teachers taught 2 years. We had no 8th grade teachers that taught 2 years. So that. And I want to talk about this with respect to your thing. What is rigorous? So our CTs are match, right? Like in your own made more famous or whatever it is, but from recent New York Times. But yeah, comparison group. A comparison group is its student, right? But they were designed to go into that. What classes are out? What are out? Our comparison, right? Right? Another idea on buy-in, right? Control trials. Teachers were forced, actually forced, and talking to this too will, right? Emotions, do it, right? The door, we're told there, right? The University District I were working, right? Teacher in your, we're really future.
We had these ideas and longer something helpful.
Seem to have part of the design that you what's wrong with them. Oh, they're in, they didn't give feedback, but they're, and if you right, but it does have, and we did mention in year two, but email and feed, not